All right, recording is rolling. It is Monday, December 9th. Today we're going to do a review on momentum in preparation for, guys, what's tomorrow in this class? In-class quiz, yeah, which is going to be on both energy and momentum. So back at the end of last week, we were doing some review on energy. We're going to do review on momentum today, in-class quiz tomorrow. You guys can bring in one paper of notes. It can be front and back, that's all right. Guys, remember to show and tell opportunity on Friday. If you want to bring in something on Friday. And then, also here at the end of last week, I did pass out this midterm study guide. There's over 100 questions here. So we're going to start going over those on Wednesday. I'll give you guys a real thorough review. Take us a few days. All right. And then the first exam day is going to be next Tuesday. So about 8 days from now. All right. So you guys ready to go? All right, so I was looking back through what questions are going to be on this quiz, make sure I got everything covered. And this one did pop up on the slides on the review, but I think I went over this a little bit too fast because I was thinking, I don't know, this one's kind of complex. Like the full story is, what's the minimum height of this hill to guarantee that it gets around a loop of this radial size, which takes this part of physics and this part of physics, right? But slow down a little bit because I think you guys can set up the energy part, right? I want to make sure you guys can set up this energy equation. So you guys go from this point A to this point B, something like that, right? Like at the top of the loop, guys, is there some minimum speed to guarantee that it gets around the top of the loop? Like if it's going too slow, it's going to follow the track, right? And that's here in this green box. That's from rotational motion, so that's not going to be on the quiz tomorrow, right? Right. Let's say you figure out what that minimum speed is, and you guys see here it's square root gr, right? Once you have that established, can you figure out how tall does this hill have to be? And we're going to go through conservation of energy to get there. So, guys, what type of energy at the top of the hill? Potential energy, right? And if it starts from rest, that would lead to the minimum height of the hill. So, what formula am I going to write for potential energy? MGH, right? And maybe I want to solve for this H, right? Like H minimum, right? By the time it gets to the top of the loop, what type of energy? Now, this H, guys, this H is relative to, you guys see my pin down here? I'm calling ground level. So that could be height 0 right there, right? Now when we get to the top of the loop, do you still have some potential energy? Yeah, right? So how much potential energy? Uh, okay, so whatever this radial size is, the height of the loop is 2r. And that would be the height from this floor down here, right? So it'd be m times g times 2r, right? And then you better have some energy left over for what type of energy? Kinetic. And what's the formula for kinetic? 1/mv squared, right? And this v could be like this v here, right? Or v squared could be v squared if you want to do that whole substitution. All right. Right. So you guys be able to construct an equation like that, right? Oh, in fact, if you guys look at, you guys remember this whole table, there was like 12 different examples here, right? There were 12 different examples, right? So conservation of energy. There you go. It's a full draw right there. All right, let's move on to momentum. Momentum. Boring. Let's scroll back. All right, so you guys remember momentum is going to be involved in collisions. Because whenever you see a collision in physics, think, okay, it's probably this property, mass times velocity, right? Mass times velocity, right? Because this would be conserved in that collision, right? Maybe not other properties like kinetic energy we'll talk about later, but definitely this, mass times velocity is conserved before and after the collision, okay? And this is a vector value, right? Ooh, guys, is that what those little arrows mean above the variables? Right, it means vectors, right? Oh, why doesn't the m get a little arrow above it? It's a scalar. Aha. Right. Now, a scalar and a vector, they could both have some magnitude, some number you can plug into the calculator, like how much, how big, right? Right. But what does a vector have that a scalar does not? Direction. Aha, direction. Right. So if something's traveling to the right or versus to the left, if we're talking about a vector value, should that be considered positive versus negative? And that'll make a difference, right? So here, I'm going to flip this off for a few minutes. Right. We're going to do some examples right here. Right, I'm going to flip back and forth today, but that'll be the end today. There. All right. So let's start with an inelastic collision. All right, we'll do perfectly inelastic. So I want to throw numbers up here that I think you guys can probably solve just in your minds, and we'll apply the equations, and you guys will see it's all the same thing. what if I have a 1 kilogram block here and a 1 kilogram block here? This one's going this way at 10 meters per second. Oh, actually, sorry, let me change that. Let's go 2 kilograms. It'll make the math a little easier. Right, 2 kilograms versus 2 kilograms. You guys see that? This one's coming to the right at 10 meters per second. This one's coming to the left at 10 meters per second. They're going to collide in the middle. Bam. And they're going to stick together. Right, so 2 kg right, versus 2 kg. Right? Right, you guys see that? Okay, guys, after they stick together, what happens next? Yeah, they just come to a stop. Yeah, that's it. Right? Is it true? Right, so same mass, exactly opposite velocity. They got opposite momentum. They'll just come to a dead stop and just stop right there. Right? That's the whole thing. Right? Right. So you guys just told me final velocity is equal to 0. We just said. Right? All right, let's try that out with the equations. So I see a collision. My framework is going to be sum of momentum before the collision equals sum of momentum after the collision. Right? There's my framework, probably for most of the section right here. Right? And I know momentum is equal to mass times velocity. I'll put this in a little thought cloud over here. Right? So now this is the summation. The sum of momentum before equals sum of momentum after. So I can add up all the momentum before the collision and after the collision. It should equate. So that could be this 2 kilogram block going at this 10 meters per second plus, right, plus because summation. Right? I got a 2 kilogram block over here. Now it's also going 10 meters per second. Right? And then they stick together. Does that make 2 plus 2 kilograms? It's like 4 kilograms. Okay. And let's say I'm solving this from scratch and I'm solving for final velocity. Now you guys told me it's going to be 0, and I think that should be the answer. Let's make sure this works. Let's see. Got 20 and 20 is 40 divided by 2. Wait. Guys, I think I wrote something a little bit wrong. Negative. Do you guys see what I left off? You guys see what I left off? Right? I left off negative right here. You guys see that? Right? That's because this is a vector and not a scalar, right? Like if I was thinking of this in terms of energy, like kinetic energy, which we'll do in a minute, then would the directions really matter? No, right, left, up, down, forward, backward, or on a pendulum going some weird angle, it wouldn't matter, right? But momentum is vector, so I have to consider right versus left. I'll call it positive versus negative, okay? Guys, now what's the momentum in the system right here? 0. I got 20 and negative 20, that's 0 kilogram meter per second. That's going to be 4 kilograms moving at some final velocity. I can solve for that final velocity. 0 meters per second because the kilograms goes away. All right. And that's what you guys said the answer was going to be from the start. Right? Okay. Right. Now let's go back to what if I had forgotten that negative sign? How could you reinterpret that? Guys, could that just be they're both traveling the same direction with the same speed? Right? If I forgot that negative sign right there. Right. So that'd be like 20 and 20 could be 40 divided by a combined mass of 4 kilograms. Wouldn't that bring you back to 10 meters per second? That's all I'd be doing. Actually, this is exactly what it could be doing. Just going like this. Hey, we're always stuck together if I forgot that negative. Okay. This is what, if you include the negative, this is actually what happens. Bam. Okay. All right. So let's do an energy check. Because before momentum, we were thinking about it in terms of energy and say, okay, well, energy is conserved all day. All right. Let's say, here, I'm going to switch to pink ink for energy. Guys, what's the formula for kinetic energy? 1/2 mv squared. Okay, so let's add it up before and after the collision. Here, I think I can squeeze it all down here. Kinetic energy before the collision, kinetic energy after the collision, and see what it is. All right, before the collision, I got 1/2 times 2 times 10 squared plus 1/2 times 2 times 10 squared. Guys, if you square the speed, even if it was a negative velocity and that gets squared, that just becomes positive again, right? Right. In fact, guys, was energy a vector or a scalar? A scalar. So I don't even have to really consider directions, right? It doesn't matter if it's moving at some weird angle. It doesn't even matter, right? I can just add 1/2 mv squared, 1/2 mv squared. V could be the speed, right? Regardless of the direction. I'm getting 200 joules. 200 joules. Right? You guys get that? Right. Now, after they've collided and stuck together, and you know how fast they're moving, what's the final kinetic energy? 0. 0 joules. Hey, wait a minute. I thought energy was conserved. Did those joules disappear from the universe? No. Where'd they probably go? Ooh, all right. So I'm going to say non-mechanical forms. If you said heat or thermal, that's probably right. Do you think if you took the temperature of these, they probably warm up a little bit? All right. How about, you guys hear smack, smack, smack? Does that sound like sound energy? I bet there's a little bit of energy. How about, ooh, what if these were made out of clay? In fact, they'd probably be more likely to stick together if they were made out of clay. Stick together? Do you think there would be a significant amount of energy that goes into deforming that clay? Like force times distance? Ooh, right? Okay. It goes into the air. So like the air vibrating. Okay, so like that, right? Yeah, so that could be sound energy. I mean, it's a little tiny amount of energy. Right? And then maybe that goes into the walls and then shakes the walls a little bit and it goes into the ground and yeah, it just shakes things around a little bit, right? Because it's just vibrations. Right? All right. All right. So you guys good with that collision? Right. So I want to do one more collision solve with you guys. Let's do a general conservation of momentum. Just a general collision right here. Right. And I'm gonna steal one off this page, which maybe some of you guys, because I made like 10 different versions of this stuff, because there's about a 10% chance you might have the exact numbers. I think you guys turned this in and I graded it, gave it back to you guys already. But look at number 3. Number 3. So I'll call this number 3 right here. Okay. And I've got 5 versus 4 kilograms. So let's go 5 kilograms here and 4 kilograms here. The 5 kilogram guy is going at 5 meters per second to the right. The 4 kilograms is at 8 meters per second to the left. So it says -8 meters per second, okay? Because on the x-axis, that would be the opposite direction. You know, bam, fly together right about there. If that's all I gave you, that would not be enough to solve it because you don't know. Are they perfectly inelastic together? Are they perfectly elastic and boing, bounce off each other? Is it like 2 half-deflated tennis balls? Like all those would be different results, right? So I have to tell you something else to be able to solve this. So let's look at this, something else. All right, so we got a collision. Maybe these bounce off each other, right? So here's my 5 kilogram block. I'm gonna have this rebounding. On this page, it says -5 meters per second. So I'll call this 5 meters per second to the left, right? And now it is exactly determinable what this 4 kilogram block is doing. I'll call this velocity of object B final. Final is in post collision, right? That's what we're solving for right there, right? Oh yeah, pause this recording and get this phone call. Come on. Yeah. All right, recording resume. All right, we're back here. All right. Okay, so you guys good so far? So here's my framework. Sum of momentum before equals sum of momentum after. Right. Here, little side thought. I want to tell you guys why I had to steal this off this page. Because if I just made up numbers off the top of my head, it's a little bit dangerous with the section. Because it's too easy to come out with something like, oops, accidentally created like ghost blocks that go through each other, even though the momentum works out mathematically. Or because if you ever, we'll run a kinetic energy check right at the end. If you ever see the kinetic energy increase, can that physically happen? Can you ever have a collision and the kinetic energy increases? That cannot happen. So if it does, all you do is very simply reverse what happened before and after. Say, okay, well, I guess what happened, or I guess got the time order backwards, right? But we're not going to run into that problem because I know I've checked this like many years ago, and I know that the numbers are going to work out. Okay, all right, so let's try this out. So sum of momentum. So that could be 5 times 5 here. So 5 kilograms at 5 meters per second. Then plus, that's the summation, plus, right? I have 4 kilograms going at, should I call this 8? Or should I call it -8? Aha, meters per second, right? And that's gonna, okay, got 5 kilograms here going at -5 meters per second, plus this 4 kilogram block going at, well, that's what we're solving for, dBi. All right, you guys see momentum accounting? It's all gonna, wait. All right, guys, what's 25 minus 32? -7. That's kilogram meter per second. Right? So that's all the momentum in the system. Guys, after the collision, Is there still -7 kilogram meter per second in the system? Yeah, that's what this conservation principle is, right? So I got -25 kilogram meter per second on one block, and the other guy is 4 kilograms some VBF. Okay, you like that? Add 25. Guys, what's -7 plus 25? Is that 18? Divided by 4 is, yeah, 4.5. So velocity B final is, got 4.5 meters per second. The kilograms went away. Speed, right? And that should be an answer choice on this page. Yeah, it's right here. All right, so that checks out. It's all good. All right, you guys good? All right, so momentum accounting, you guys can solve. This is just a general collision right here. All right, while you guys are finishing digesting that, I'm going to do a kinetic energy check. So here, I'll do it also in this corner down here. So what's kinetic energy before the collision? What's kinetic energy after the collision? Okay. Now, kinetic energy, is it probably going to decrease? Yeah. All right. The other option is it could be the same. If it happens to match, guys, if it's the same after as before, you know it's a what kind of collision? Yeah, perfectly elastic, right? Which would be really similar to this right here going on, right? But that would be perfectly elastic, which probably is not the case. I don't know. We'll find out. Let's see. So I'll do 1/2 mv squared plus the other 1/2 mv squared. Right? I don't have to worry about negatives because this is a scalar. It's all going to add up. I'm getting 190.5 joules. Right? So like 190 joules. Right? I know after the collision, it cannot be more than that. It can only go up to that number. Let's go 1/2 times m times this v squared plus 1/2 times this m times, and we just found v final for the second block. You see how boing, it's going to rebound, it's going to bounce back. Okay, let's see what this is. It's got to be somewhere between 0 and 190. Okay, 103 joules. Yeah, do you guys see the kinetic energy went down? Right, right. All right, same as before. It didn't disappear from the universe. It just turned into non-mechanical forms. Okay. All right. So you guys go with these collisions so far? It's good. All right. Let's go back to this right here. All right. So see what we got. Now we just solved 2 examples of this closed system. Sum of momentum before equals sum of momentum after. Right. Now later on today, we'll look at an impulse example of a bat hitting a ball. That's this change in momentum. So if you start out with some momentum, you have an impulse that's going to change the momentum. You end up with some final momentum. Okay. Impulse is a change of momentum. So that'll show up later. Okay. And so here's a general collision. Hey, that's what we just did. Right? If you add up all the mass velocity bits before and after, they have to equate. Now keep in mind, momentum is a vector quantity. So right could be positive, left could be negative. Right? And you have to plug in the numbers that way. That's the only way it works. Okay. Here's your perfectly inelastic collision. That's the first one we solved today. The 2 blocks that stuck together, made one giant mass. It's some common final velocity. Right? So it starts out the same as the general, and then they stick together. Okay. You can also have a backwards version of this. Do you guys remember like solving the grenade question or the throwing a snowball question on an icy surface? Right? It's like that. That's just this backwards. Right? Perfectly elastic. So if I ask you a question like this, it's probably not going to be the full math, right? Even my AP students, they usually a little careful about how I'm solve this whole thing mathematically. But what I would want you to know is the concept of what's conserved. So momentum conserved. Is that true for all collisions? Is momentum conserved? Yeah. Right. Now, what makes an elastic collision special is that what else is also conserved? The kinetic energy. Okay. The kinetic energy. Right. I think the Kahoot question version of this you saw, it was one of the all the above answers. It was like, yes, kinetic energy is conserved. That's what makes this elastic, which also implies some other things, like the objects are not going to warm up. They're not going to change their temperature because that would divert some of the energy to thermal. So that can't happen. The objects won't permanently deform because some of the energy would have gone into that. So that can't happen either. Right? Okay, so that would all be true. It's all implied. right. Here's like a full table. You can get like a spectrum of collision types. So at the top is perfectly elastic. That's like perfectly bouncy. Boing, boing. Then you have some general collision. I think last week you guys were dropping tennis balls. They were bouncing off the floor. It didn't stick to the floor. It didn't bounce up to the original height. It's somewhere in the middle. We just solved that anyway. Then perfectly inelastic, they're going to stick together. Right? So there's your full spectrum from the first to the third row. Right? Do you guys see every single one of these momentum is conserved? Right? But something different with kinetic energy. So kinetic energy is only conserved for perfectly elastic. In general, it decreases. Well, it could stay the same, but if it does stay the same, it just goes back to elastic. Right? And for any time two objects stick together, kinetic energy will always decrease. Right? And you can show that. Right? Right. This very last row, explosion. That's just perfectly inelastic turned around. That's the grenade exploding. That's do you guys remember that Magic School Bus clip? She threw the ball forwards and she was then sliding backwards towards second base on a frictionless field, right? I think it's the first one I solved with the guys in class was that type. We're trying to figure out how fast does she slide back towards second base, right? That's just this last row, right? And for anything like that, do you see the kinetic energy actually would increase? But that energy, again, comes from somewhere. So in the case of the grenade explosion, maybe the chemical reaction within the grenade, or if you're throwing a ball, doesn't that come from your muscles? Is where the energy comes from. All right, so you guys could figure that. All right. Ooh, do you guys remember collision carts? You guys were sliding those carts around. You guys had two labs. One was right before the Thanksgiving break. One was right after the Thanksgiving break. You guys remember collision carts? You see that? Okay, I think this one's a little bit in the weeds, but if you're curious, what's the relationship between kinetic energy and momentum? There's a way you can that. Right. Ooh, how can you quantify how bouncy is a collision? So if I scroll back a few slides, here we go. You guys remember saying that like there's a spectrum of collisions, right? How can you quantify where you are? So it's called coefficient of restitution. You say, what's the difference in velocities post-collision compared to pre-collision, right? Take that ratio, right? Here, let's do some numerical examples here. Suppose two objects collide and stick together. Guys, if they stick together, what is the difference in velocities between the two objects after the collision? 0. Yeah. It could be they come to a dead stop, at rest. That would be 0 minus 0 is 0. Or even if they're both moving, like 7 minus 7 is still 0. Do you guys see the numerator would be 0 if they stick together? Which means the whole fraction would be equal to 0. Okay, that's one boundary condition. That's perfectly inelastic if they stick together, right? What do you think this fraction is equal to for the other extreme? Perfectly elastic, like Newton's cradle, like boing, boing, boing. What do you think this fraction comes out to? 1. Right. Now, when you guys did this lab, I had you guys do this version where you bounce the ball off the floor. Is that so? Did you guys, for your answer, get something between 0 and 1? Maybe 0.5, 0.6, 0.7, maybe something like that. Right? How bouncy is the ball off the tile floor? You guys had different kind of balls. There were racket balls and tennis balls and little bouncy balls. Right? So all different answers. Right? But okay, something like this. All right, let's go through this. So, do you think there's some the floor? The floor is not moving, right? The floor of the earth, say relative to the ball or something, right? Inertial frame of reference. So that's one of the objects. The two objects here are the ball on the floor, the ball on the earth, right? We're going to say the floor is not moving. Okay? Do you think there's some crash speed and some rebound speed? And the difference between the floor and the crash speed is the crash speed. And the difference between the floor not moving and the rebound speed would be the rebound speed. So, do you guys see this fraction right here? Coefficient of restitution. It follows from the last slide. It's all right. Rebound speed compared to crash speed. That's what that would be. Right. Guys, if you drop this ball, can the ball ever bounce up to higher than the original height? No. Right. So it could stick to the floor. I think I had like a ball that did that. It could bounce up anywhere up to the original height, but it can't go higher than that. Right. All right. So let's try a couple examples here. All right, for our coefficient restitution. All right. So let's look at this bouncy ball example. This bouncy ball. Okay. Let's say you drop it from a height of 100 centimeters, or if you like, you'd call it 1.0 meters. It's gonna boing. Okay. Let's say it rebounds to a height called lowercase h of 60 centimeters. Or if you like 0.60 meters in terms of meters, right? Okay. All right, we're going to try coefficient restitution from both points of view. from the fraction point of view and that shortcut that you guys did on your lab. So the original definition was, all right, well, when this ball's about to crash, it's got some V crash. And when it rebounds, I bet it's going to rebound a little slower, call it V rebound. Okay. And the other object is the floor, which is not moving. So we're going to say post collision, what's V rebound minus V floor over, and then I'm going to swap them the other way on the denominator so that this whole thing comes out to a positive value. Okay. V floor minus V crash. Okay. And then the shortcut version of that turned into square root rebound height compared to drop height is what you guys did, but no, let's see if this all works out. Okay. So guys, if you drop something 1 meter, how fast does it crash into the floor? Okay, so yeah, I know it's picking up about 10 meters per second squared. Does it for 1 meter. Guys, if it's falling 1 meter, is that equal to, more than, or less than 1 second of falling? A lot less than a second. Hey, let's do the Galileo question right here. Let's do energy conservation. Let's go back a little bit. Sum of energy at the top equals sum of energy right as it's about to hit the floor. So what kind of energy at the top? All right, so there's your MGH. What kind of energy right as it's about to hit the floor? 1 FMV squared. Oh, do you guys notice I never gave you the mass of the ball? Right, and when you did the lab, I never had you measure it with a scale either. Right? So that's irrelevant to this property, coefficient restitution. Right. And solve for this V right here. Times 2 square root. You guys get square root 2GH. Hey, square root 2GH. Wasn't that the answer to the Galileo question? Right. All right, let's get a speed. Crash speed equals, try this out. Square root 2, 9.8 meters per second squared, and 1 meter. All right, square root 2 GH. 4.43 meters per second. Okay, so there you go. Oh, that's true for any object. If I take this object right here, right now I'm holding it about a meter above the tile floor. If I just drop this 1 meter drop, does it crash into the floor that fast right there? Yep. Okay. Suppose there's a short ledge and you jump off the ledge. Well, it's like 1 meter tall. How fast are you going to crash into the ground? About this fast right here. Okay. Okay. Oh, how about V rebound? Is it basically this just turned around and this capital H could turn this lowercase h? So I get square root 2 G, and then this would be 0.60 meters, because notice in my equations I'm putting in everything in terms of meters, right? Right, so all my units are consistent. So square root 2 GH. Getting 3.43 meters per second. Okay. All right. So I got this number right here, this number right here. All right. So let's feed those into this equation. Coefficient restitution is fraction the rebound speed minus the floor, like post collision. So how fast? What's the difference between the floor and the ball? Okay. That would be 3.43 meters per second minus 0 meters per second. Okay. All divided by the floor, 0 meters per second. Okay. Now here, if I'm treating this V as a vector value, the ball does reverse direction, right? So I'm going to say minus a negative 4.43 meters per second. You guys see that? Did this negative go away? Point. All right. So what is this? 343 compared to 443. Looking at 0.77. There you go. Okay. So what that means is this ball off this tile floor, whatever the crash speed is, the rebound speed is going to be 77% of that. Okay. The rebound speed is 77% of the crash speed. Okay. Let's try it the other way. The other way is, here's the shortcut formula that I was walking you guys towards. Okay. So square root 2gh compared to the other square root 2gh. Now they're different h's, but it's the same 2g. The 2g cancels out, and you just get the square root of the ratio of the heights. That's what works out. Let's try that. So coefficient of restitution could be square root of the rebound height compared to drop height. Okay. Square root 0.6, like that. Okay. Guys, when I hit enter, what's the only number that can show up on my calculator? 0.77. Right, had to be, right? Because we just did it with more steps, right? But you guys see it has to be the same thing, right? Right? All right, guys, good day. Oh, well, I got some paper out. I had you guys do a graph at the end, and we never went back and exactly debriefed that. But I had you guys drop different heights and say, what's the rebound height? So what's rebound height compared to drop height? You guys remember we made a graph? Right. What shape did that graph take? I think it was linear, wasn't it? Wasn't linear? Right. Like maybe you did a bunch of different drop heights and rebound heights, and it came out like a straight line graph like that. All right. Just to fill in that blank right there. All right. Let's go back to PowerPoint, where we are. All right. So you guys go with coefficient restitution. How bouncy is the ball? All right. There's your lab. Okay. Just talk about that graph as a linear graph. All right. Ooh, impulse. So impulse is a change in momentum. I use delta P, change in momentum, right? Which if you have a constant mass, that'd be m times delta V, mass times change in velocity, right? Like this ball right here getting hit by the bat and stuff like that. Right? And how do you get an impulse? By applying a what for a what? It's on the axis of this graph. A force for some time, right? Force for some time interval, right? Now, oftentimes you'll see these graphs look like triangle shapes, like the force builds up and then dissipates, so it looks like a triangle. Right? Doesn't have to, though. You could consider the average force, and then this graph would look more like a rectangle shape. But if you have a force versus time graph, the impulse is the area under that curve. It's like the area of this triangle, the area of this rectangle. Do you guys see those are the same area? That triangle and that rectangle with the average force value? Okay. All right, so let's try this out. We're going to do an example of a ball getting hit by a bat. All right, so impulse. So here's my bat set up right here. Right. Have a ball. Say the mass of the ball is 0.15 kilograms, because that could be a baseball. Okay. Let's say it's headed towards the bat at 20 meters per second, and then bam, it's hit by the bat. It's going to rebound back away at the final, right? And that's maybe what I want to solve for, like that. How fast does it rebound back away? Okay. So my framework is going to be the initial momentum of the ball plus the change in momentum, the impulse, is the final momentum. Hey, that's like an open system type equation, isn't it? Right? Okay. Oh, whoops, I forgot to throw some more numbers on here. More numbers. Right. I need to give you like an average force value, or I could give you a graph. Let's say the average force is like 800 newtons, and it lasts for a time interval, so delta t time interval of 0.01 second. There you go. Okay. Now we can solve this. Right? Okay. So the original momentum of the ball is that mass times initial velocity. And guys, this impulse right here, this impulse is what times what again? Force times time? Force times time interval? This is the average force. Okay. That's going to result in the baseball with some final velocity. And that's what we want to know. Right? How fast that baseball head towards the outfield. Okay. Right, guys, it. Okay. So let's plug some numbers in. I got a 0.15 kilograms baseball going at okay, now here's where I have to be careful. Guys, I'm talking about vectors. You see the ball was headed towards the left, and it's going to be hit back towards the right. I have to consider negative and positive. Can I call it to the right positive? Should I do that? And if I call it right positive, then left would be negative. So I'm going to call this negative 20 meters per second. You guys see that? Because it was headed towards the left. But this force is forcing it back towards the right. And hopefully it ends up rebounding back towards the right. So like an average force of 800 newtons for 0.01 seconds. That's going to result in a 0.15 kilogram space ball. Doing something over here. Okay. I think this is like -3 kilogram meter per second. This is like 8 kilogram meter per second. 0.15 kilograms at some VF. Right? You guys finish the algebra? Guys, what's -3 plus 8? 5 divided by 0.15 kilograms. So the kilograms goes away. I'm getting a final velocity of 33 meters per second. There you go. There's how fast the baseball leaves the bat going off towards the outfield. All right, you guys can figure that out. Impulse over. All right. All right. All right, there's a few more slides I have for you guys and one last big puzzle to solve. All right, so here we go. All right. Ooh, inelastic versus elastic. Suppose you have either a bullet or a piece of putty, something that collides inelastically with this bowling ball. Suppose it comes in with 5 units of momentum. So m times v could be 5 kilogram meter per second. Okay? Then it collides, sticks to it. Does the whole bowling ball bullet system roll off with the same 5 units of momentum? Yeah, that would be conservation of momentum. Right? What if instead you have a bouncy ball? The boing bounces off. Say it comes in with the same 5 units of momentum, but then it rebounds. Boing. Now it's going like 3 to the left. So 5 to the right, 3 to the left. How much momentum was just imparted to that bowling ball? 8. Because 5 minus -3. That's a difference of 8. Okay? Which bowling ball rolls off faster? The one on the top or the one on the bottom? Yeah, this elastic one on the bottom. Well, more elastic. Definitely be more elastic, wouldn't it? Faster. All right. I'm not going to ask you a 2-dimensional, but if you ever see this in the future somewhere, here's the guiding principle, is that along each axis, the y-axis, the x-axis, momentum is conserved along each direction. Okay, so then you can solve it from there. Right? These 3 slides are all new, and they all kind of go together. They get at the same idea. So I'm kind of scrolling back and forth between these 3 slides. So if you have 2 asteroids collide in deep space, if you just focus on the center mass of the 2 asteroids, you'll never actually know when the collision happens. If you throw a ball on a frictionless surface, it's just the exact reverse of that. Okay. So again, I think this is the first one I solved with you guys. This is the magic school bus question right here. So mass times velocity of the ball one way, mass times velocity of the pitcher the other way. It would zero out because they started with 0 momentum initially. And that center of mass never moves. The center mass of the ball and the pitcher always stays right on top of the mound. Okay. And then you guys got a grenade version of this. If the grenade explodes into different parts, the center of mass just keeps following. Right, doing what it was doing. Okay, got that. Okay, and that in reverse. If you film that and put it in reverse, it would look like an inelastic collision. All right, here's the last one I'm doing with you guys. Ballistic pendulum. So the classic question is, what's the firing speed of the bullet? There can be different variations on this, but I'll do the classic version. All right, so that bullet is going to collide inelastically with the block, and it's going to set it up some height change. Okay? Now, if you know the masses and the height change, you can solve the speed of the bullet. But you need to do this in 2 halves. The first half is this conservation of energy in green. Say, well, how fast did the block get going so it can swing up to that height? And then you go back in time to momentum. That's in here in this gold box. Say, well, how fast was the bullet then going to send it off going in the first place? All right, I got just enough time. I need to switch over and solve this on paper, though. All right, so let's solve this one on paper. Here we go. All right, so set up a pendulum right here. Let's say the mass of the block is 1 kilogram exactly. Okay, 1 kilogram. Okay. I got a bullet. Let's say the mass of the bullet is like 0.01 kilograms. I'll call it 10 grams if you like. Okay. And it's got some velocity. I'll call it V bullet. Right. And that's what we ultimately want to know. Okay. So chronologically, the first thing that happened is going to be the last thing we're going to solve. Okay. The bullet's going to stick in the block. And then they're going to swing up. There's going to be some height change here. Call us H. Right. Okay. Now you guys know that you could calculate the H from that L and that theta. You guys remember that? Right. Oh, I have it right here. You guys remember this? Right. You guys seen this a few times? We've been through the geometry a few times. It ends up working out to this, right? Right. Right. So maybe you can go back and review that, or if you watch this video, maybe record on that frame right there. But I'm going to go ahead and give you guys a height value. Let's say this is like 0.11 meters or 11 centimeters, if you like 11 centimeters height change, right? Okay. So right there, there's enough information we can solve what was the firing speed of the bullet. Right, we're going to solve this reverse chronologically. So the last thing that happened is it swings up to some height. That sounds like conservation of what? Energy or momentum? Energy. Sum of energy at the bottom equals sum of energy at the top. And what type of energy down here? Getting it in motion? Kinetic. 1/2 mv squared. I messed up already. Right. Let's do block plus bullet as the mass, although it's not going to matter here in a minute. Okay. And then it swings up to some height, mgh, but I'm going to consider block plus bullet and then gh, right? Although if you made the same mistake, or I forgot, oh, wait, I need to include both masses because they're stuck together, it wouldn't matter anyway because it's going to cancel out there, right? Is that true? Okay. Let's solve for this v right here. So this v is times 2 square root 2gh. Is that true? Okay, let's get a hard number on that. Square root 2, 9.8 meters per second squared, 0.11 meters. Now, if I told you 11 centimeters, you guys could convert that to 0.11 meters, right? You see that? So that all the units are consistent. We'll keep everything in base SI units. Square root 2 GH. I'm looking at 1.47 meters per second. Okay. Now, what does that mean? See if you guys are following. Guys, is that the firing speed of the bullet? Do I have the world's slowest gun? Or the world's least lethal gun? No, I don't think so. Right? So, guys, this is the speed of what? This is the speed of the block down here so that it can swing up to this height. That's all we found. Right? Or how about this? If you did this pendulum lab, you pulled it up so there was a height change of 11 centimeters. You let go. Would it be going that fast down here? I mean, that's just the reverse, but it'd be the same number. Right. But we got to figure out how fast was the bullet fired so that it got the block moving that fast, right? Right. And that's going to be conservation of what? Momentum. Aha. In fact, that sounds like a perfectly inelastic collision. Sum of momentum initial equals sum of momentum final. And guys, all the momentum was provided by the bullet. So mass of the bullet times velocity of the bullet. Oh, hey, that's what we're solving for. There it is. So what we're solving for is now within view. Okay. And then when it collides and sticks, is it going to make block plus bullet moving at some speed? Okay. How fast? How fast is it going after the collision? Right there. That's what we just found. Right? Right, guys, that's what we just found. So I think we got the numbers here. 0.01 kilograms bullet times V bullet that we're trying to solve for. So there's the question. Okay. Then block plus bullet. There's the block, there's the bullet. It's all together like 1.01 kilograms. Going at 1.47 meters per second. Right, just like that. All right, so that times that divided by that. 0.01 times 1.47 divided by 0.01. Okay, I'm getting V bullet is 148 meters per second. Ah, is that the firing speed of the bullet right there? Yeah, there's the firing speed of the bullet. And that's a wrap on that recording.